and then you can understand what's going on in each of the regions. So we're going to cover the remaining liquid phase diagrams, and then we're going to get into solid phase diagrams. So what is the definition of a homogeneous mixture?
Yeah, it's like clear all the way through, the same all the way through.
It's the same all the way through, so it doesn't matter where you sample it, right? You don't get a different concentration of species at the top or the bottom or in the middle, okay? Now, it doesn't say anything about that mixture being a solid or liquid. It just means that it's homogeneous. So this right here, this brass key, is a solution. It's a homogeneous solution. It just happens to be solid. It doesn't matter if I sample the tip or the back or the middle, it's the same percentage of zinc and copper to make this brass key. And so we're talking about solid phase diagrams in the miscible region, what we would call miscible, in liquids, mixtures, miscible, acetone and water, we can see that. But in the solid as well, for brass, you can go from pure copper to pure zinc and all the concentrations in between. So it's not a compound. It doesn't have a defined molecular formula. It has percentages. It's a homogeneous mixture. It's a solution. And so we have solid solutions, and we'll talk about the phase diagrams of solid solutions this morning. And so here's one that's interesting. This is palladium metal, and a lot of these metals, like palladium, can be highly hydrided. So hydrogen will react with these metals and actually will dissolve into the metal. So in these different regions, in this phase diagram, it has an upper consolid solution temperature. And so this would be, below this you would have phase separation in this region. This is the mole fraction of hydrogen in palladium metal. And so on this side you would have highly hydrided metal, and over here you would have mostly not quite pure palladium, but dirty palladium, a few atoms of hydrogen roaming around in the metal. So this is just an example of, above this, some sort of homogeneous mixture of hydrogen and palladium, and down here you have a split with two different species. Now this right here, this highly hydrated metal, may have a different properties. It may break easier, may be brittle. And so hydrogen and metal is an important, this phase diagram is sort of just an example that the mechanical properties of metal can change in the presence of hydrogen. And so hydrogen and metal sometimes can cause mechanical problems. Let's go back to the liquid ones. We talked about an upper critical solution temperature or upper consolid temperature. You can also have a lower critical solution temperature. So this is a bizarre situation. This is triethylamine in water. So on the far right, you have triethylamine, and on the far left, you have water. Now, if you think about triethylamine, there's a potential for a weakly bound hydrogen bond because you have that NH2 group on the nitrogen. So if you need help, just go ahead and draw it. You've got the nitrogen here with the lone pair, and then there's an ethyl group coming out. There's an ethyl group, and going back, there's an ethyl group. And so you have these three arms on the nitrogen, and then you have this lone pair. Well, the motion of these arms is going to be temperature dependent. So at low temperatures, water can get to that lone pair and hydrogen bond, and they can mix at all concentrations. They're miscible. But as you warm it up, those arms really start to go crazy, and they disrupt that hydrogen bonding. And so then you have phase separation. You have an organic layer and an aqueous layer. And so this is an example of a lower consolid temperature. Below that temperature, things have calmed down. They can mix and hydrogen bond. Above that temperature, the hydrogen bonding is disrupted.
Would this still be above water's freezing point?
No, this would be liquid. So below this would be the solid phase diagram. And so we're going to have, at the end, we're going to put all three of these together. The solid, maybe this two-phase region in the middle, and then the vapor-liquid equilibrium. So we're still a TX phase diagram, but now we're kind of lower than the vapor-liquid is at the top, where you have the azeotropic behavior. Now we're in the middle region where it's all liquid, and you may have phase separation, so 2 layers, and then down below you start to freeze things. This is nicotine in water. That's crazy. Yeah. So it has a lower constant temperature and an upper constant temperature. So there's this region in the middle of temperatures where you have 2 layers, and then you cool it down further and it goes back to 1 layer. Bizarre. So nature is strange. And when you're dealing with phase diagrams, it's sometimes hard to understand. You just are mapping out the behavior of the real system. So these are all based on experiment. And so it's this 2-phase versus 1-phase is really based upon whether the solvents like each other, okay, or not. Water likes itself a lot because it can hydrogen bond. Each water molecule can hydrogen bond with 2 others. Okay, it can receive 2 hydrogen bonds and give 2 hydrogen bonds. It can donate 2 protons and receive. So that's a huge thing with water bonding to itself. If you disrupt that at high temperatures, then you have miscibility. So down below, you might have so the way I explain this is you might have some hydrogen bonding of water to nicotine, which will be very weak. But at a certain temperature, then that hydrogen bonding to nicotine is not favorable, and so you get phase separation. And so in this region, water likes itself way too much to let nicotine in. So you have 2 layers. But then, as you get high enough, okay, now this would be under pressure because this is 210 Celsius, so this would be at a higher pressure. Above this pressure, you've disrupted the hydrogen bonding of water with water. And so now water is not able to hydrogen bond with itself consistently, and entropy takes over, and you have 1 layer again. So entropy is always trying to drive mixing, but intermolecular attractions, that enthalpy term, is trying to oppose mixing. And so you have different regions where that Gibbs energy of mixing goes positive, and you get separation. So if you were to be given this chart without the P1 and P2, could you figure it out? Like you see this circle in the middle, what would you do with that? Again, start with the axes. You have temperature on this axis, mole fraction on that axis. Going all the way over to one side, this is nicotine, pure nicotine. That's 1 phase. And so that tells you this region right next to that pure substance is going to be 1 phase. Same over here with water. This is pure water. Pure water is 1 phase. And so next to pure water would still be 1 phase. You get over here, you hit this line, it's going to be 2 phase in between this region. Now, let's pick this isopleth right here. Okay. That's going to be your fulcrum for the lever rule. So whatever concentration you have, if we're 60% nicotine in water, then as you march up this 2-phase region, that 60% will be the Z composition, or Z nicotine, and then you have these 2 layers, and you use the lever rule to figure out how much of each layer you have and how many moles of each substance you have in each layer. Okay. If you wanted the best separation at this pressure between water and nicotine, you would pick this temperature here, because this is the farthest apart they are. And so that would be the purest 2 layers that you could get. If everybody kind of see that. If you're down close to this consolate temperature down here, the 2 layers are not that different. One is 50-50, the other is about 70%. So it's still a lot of nicotine in the water and a lot of water in the nicotine. But if you wanted to separate these 2, then you would want to be up there at the temperature region where the layers are most different. Anything I can clarify with this? This is probably the strangest one to look at. You see this circle in the middle. What is that? Okay.
So for the other ones, how would you determine what's the most pure? Because if they just go up until the next diagram.
Yeah, you would just try to map it out to see if it keeps going up. But yeah, if it's getting more and more pure on each layer, then you would just go as high as you could go, whatever was reasonable. Yeah. Or if it's getting cold, you might do a cold separation because the layers get more and more pure as you go down in temperature. That was an earlier phase diagram. You would just want to do a cold separation then. So you would just chill everything. And by chilling it, you could maybe make a huge difference in the purity of the two layers. You've heard of cold filtration, same kind of thing. Some things are, the solubility, is, at cold temperatures is just really low. And so you cool it down and filter it cold. Supposedly that's like Coors, cold filtered. So I don't know that.
Since it has a low constant point, when you freeze it, it's all going to be one phase then.
Now the freezing behavior is bizarre.
So it gets different.
Yeah, so the freezing behavior is weird. Okay, so we'll talk about that. One substance or another starts to freeze first. So when you have a mixture, freezing it out is strange.
Interesting.
Yeah.
It's like reverse
If
distillation.
we did something like similar to nicotine, like caffeine, would it have a very similar phase diagram also?
It's a good question. I don't know. I only have the ones really that came with the book, and so it'd be nice to go explore and see what other kind of phase diagrams there are. And once again, they're getting easier to find now on Google, Google Images. You just type in phase diagram and go to the Images tab, and you get thousands. And so it's pretty cool. Most of them are like boiling, vapor liquid equilibrium phase diagrams. You do have some PT diagrams and so on. But you'll be surprised at how complex they are. Well, let's just do it. Let's just want to talk about it. I want to do a Kahoot too, so. That's a fun little Google Doodle if you want to do that sometime in your spare time. You get to get artificial intelligence to compose a song for you. Yeah, so some PT diagrams. So yeah, here's one. So we're going to get into the solid liquid phase diagram. So this is a solid liquid phase diagram. So these are melting points up here. So we'll get to those next. You see, it's kind of crazy, isn't it? Let's try to find some liquid ones. There's an azeotrope. Look at that one. What the heck? Yeah. Weight percent copper. What is this? Aluminum copper phase diagram. Look at that thing. That's awesome.
Oh, too
Kind
much.
of looks like a building.
Yeah. This is
Gold.
gold, yeah. Gewichtprozent gold. I don't know what that is. I don't speak German. Aluminum and zinc. Thank you. That's awesome. Yeah, I'm not seeing very many liquid ones, like the nicotine one. Okay, this is a weird one. Oh, that's climate prediction. What is it? No, not wrong class. Let's see. Yeah, so you can look at these, and it'd be nice to just drop into any one of these phase diagrams and see if you can understand what equilibrium lines we're talking about and where the different phases are. So, okay, so then this is let's now add at least a couple of these together. So here on the left we have distillation of a partially miscible liquid, where you have phase separation in the bottom part of the liquid region. So let's start over. Go to the axes. We got a temperature axis. That means at the very high temperature we have gas. Okay, so gas at the top. Then you have vapor liquid equilibrium, and you see an azeotrope. Is it a high or low boiler? It's a low boiling azeotrope, because you see the boiling point of the azeotrope is below the boiling point of A and B. Where's the boiling point of B? So you look at the x-axis, mole fraction of B, xB. This is pure B. This is the boiling point of B. Okay. At whatever pressure this is. This is for a given pressure. We could assume it's 1 atmosphere, but it might be a high pressure phase diagram, like that nicotine one. Okay. This is the boiling point of pure A. Okay. This is the upper consolate temperature. For the liquid, you have 2 phases down here. And so if we start with A, this is kind of fun. We start with A in our pot, and we do a distillation, a simple distillation, meaning just one step. So we boil it and collect the vapor that comes right off. And so you come up here, it boils. This is the liquid boiling point. What's the vapor composition? Straight across. Okay, because this is temperature. So this is the composition of the vapor above this liquid at that temperature. If you condense that vapor, it comes down here. If you stop it here in the collection flask, it'll be miscible. But if you let it cool all the way down back to the original temperature, you have 2 layers. That's kind of weird, isn't it? You have a single layer system in your pot, and you distill it, and over here you have 2 layers in the collection flask. It's just the way the phase diagram works. Okay. If you do a fractional distillation, what will the ratio of the layers be? Okay, you would go all the way down the hill, condense, re-evaporate, condense, re-evaporate, condense. Yeah, so it'd be the azeotrope, and it would come down here, and in your collection flask, that would be the fulcrum. And you would have this layer and that layer. So you'd have much more of this layer. Your layer that you got in your collection flask, the A layer would be more, have much more A than just the single distillation. Single distillation would have mostly B still and a little bit of A. But if you went ahead and did a fractional distillation, you would collect the azeotropic composition, and that azeotropic composition would be a 2-layer solution. Okay, it'd be heterogeneous. And when it's heterogeneous because I sample the top and I get 1 layer, I sample the bottom, I get a different layer. 2 different compositions. Okay. Sometimes these intersect each other, so you don't really have an azeotrope. You have this thing. So see how the 2-phase region comes up here and hits the vapor equilibrium business. And so you've got a problem with this one. There's really no azeotrope. So anything between this region here and here boils at this temperature. So this 2-phase liquid will boil at this temperature in between these compositions. If you're over here almost pure B, then it will boil a little bit higher. Okay, so this is a homogeneous solution. It boils here, then it hits that and then drops down, and you've got the 2 layers. Okay. This would be the pure boiling point of B. This is the pure boiling point of A. And this is the vapor composition curve. And these are the liquid layer composition curves. Anything in this particular chart that you want to ask about? Sort of confused about what's going on in any of the layers? So you should be able to explain, like going from A1 to A2 to B1 to B3 or whatever. You should be able to tell me, that path of simple or fractional distillation, what's going on.
That line that goes through the azeotrope there.
Yeah, and so let's think about this one for fractional distillation. It really doesn't get you much over simple distillation. So this comes up, the first condensate hits here. This is going to boil right here.
Okay, that was my question.
It's going to boil, and then the boiling point, it's going to, let's say it recondenses. This is the vapor composition. Recondenses, but you still got, these 2 layers. You're going to be stuck in between these regions all the way up the fractioning column. And this will always be the condensate temperature. It's that highest temperature for the 2-layer solution. So, yeah. that's given an E because that also looks like in a solid phase diagram what we call a eutectic. And so we'll look at that when we get to the solid phase diagrams. This is just talking about the pot moving towards the pure substance. So this eutectic mixture, again, is the two-layer system. It's kind of weird because the boiling point of each of those pure layers, like if we were over here, if we just separated that layer, this is kind of bizarre. So we've got this condensate at B3. It's got this layer, B3 double prime and B3 prime. So we separate these two layers with the sep funnel, and we stick B3 double prime in a flask and boil it. It has a boiling point right here. Right? What's the boiling point of this layer? It's right there. Okay? We take the other layer, put it in a flask, and boil it. What's the boiling point of that layer? It's here. Okay? But I mean, it's coincidental that it's the same. It doesn't have to be the same. Okay? But we mix those together, and the boiling point is this line right here. So the two layers in contact with each other have a lower boiling point than any one of the pure layers. The layers really aren't pure, but they're homogeneous layers, you know. And so, again, what is the definition of the boiling point? It's just that the pressure in the flask equals the ambient pressure. So you could have 3 layers, but if the pressure in the flask is equal to the ambient pressure, then you've got a boiling solution. It doesn't have to be homogeneous to boil. Okay. So it's just kind of strange. The things you haven't thought of, I can tell. Every time we get to this in this year, people are just kind of looking lost. I'm like, I thought I understood stuff. But just thinking about layers of solutions and how they behave, I mean, we don't even really think about it. We go into organic lab and we stick something in the pot, stick it on the heating bath and turn the heat on. We don't really get in there and stare at it and see what's going on. That's what a P chemist does. So if you're fascinated by bubbles and two-layer solutions, you may be a P chemist. It's just like the Jeff Foxworthy thing. If you think phenanthrene, and water look the same, you may be a P chemist. So they have the same point group. Let's go down in temperature further, and let's start to freeze things out. So here we are at A1, and mole fraction of B, temperature on the y-axis. So we're cooling this down, and we get to A2. What starts to happen? We have this tie line here.
Yeah.
This is the lever rule line, okay? We call it a tie line. Something starts to solidify, and it's pure B that starts to solidify. And so we keep cooling it down, but we have so much B that B starts to make solid B. If we pull B out of this solution, then the liquid gets rich in A, because we're pulling B out preferentially. And so as we continue to cool this down, now the liquid is depleted in B. It's it's closer to A, right? Because we're pulling pure B out. And so this is the amount of solid B, and this is the amount of liquid above that, and this would be the fulcrum for the lever rule. So we just keep cooling it down until we get to this point, and we have the eutectic, the lowest melting point for this mixture, and this is when pure B and whatever the remaining amount of A is starts to precipitate. And so then we have a lever rule between pure A and pure B. So we have mostly B and little bits of A precipitating out and making a solid. And it will sit there at the eutectic temperature until all the A is solid, and then we're just cooling the solid. And you don't have any composition changes from here on down because it's solid B and solid A at the proportions given by the lever rule. Pretty easy, right? It's just the weird thing is that liquid line moving away, from our isopleth. So we're following an isopleth and cooling it down, and the liquid line starts to depart as we start to freeze out some stuff. Okay. Now this is not what you would say your normal of behavior, we could go an opposite direction and have a melting point. Okay? And so if you could see visually, say in a capillary, like we do in organic lab, right? If you could see in a capillary the solid and the liquid, so you've got solid crystals and you start to warm it up, at this point the crystal would get wet and you would see some of the liquid form. And yet you could still see solid, because you see solid over here, and you still see solid, but it's getting wetter and wetter and wetter. At this point, the solid's all gone. But you have this melting range that's this long. That's horrible. Why is that horrible for an organic chemist who wants to report a melting point for their substance? It's a huge melting range. It started melting down here, but it was the crystal, the solids that I could see with my eye weren't completely gone until way up here. And so what does that tell you? It's impure. Right? You're doing purity check with your melting point. How narrow is the melting range? And this has an enormous melting range, because look how impure it is. It's not pure B. It's way over here. It's like, 80% B, 20% A, so it's really impure. And you have this really long melting range. What if you had pure B? It wouldn't melt, wouldn't melt, wouldn't melt, wouldn't melt, wouldn't melt. Pow! It melts. And so that narrow range would tell you have a pure substance. So if you have a pure substance, there's a distinct melting point. If you have a mixture, it's a terribly long range of melting. So you're melting some of that B and it's mixing in with the A, and you've got this really long development of the liquid. Okay. Now you might have a decently good melting point of the eutectic here. So if you were right here, you're coming up, then at this point you would pause, and all of the A and B solid would melt at the same time, and then you would have a sharp melting point. So eutectics have a sharp melting point, and pure substances have a sharp melting point. And anything in between would have a long, slow melting point, melting range.
How can we distinguish the two sharp and melting points?
Yeah, the different temperatures. And so you see that eutectic, you're like, whoa, I thought B had a melting point of 250, and it melted at 180. And so these solid solutions that we have, so this is a solid solution down here, some of them can have melting points that are dramatically lower than their pure melting points. Dramatically lower. And that's what we use for solder. We want to melt metal at a low temperature to bond metal to metal. We want the legs of our little circuits to bond to the circuit pads, and we want that to be a metal connection for conductivity. But we need a metal that melts so low so that it doesn't cook our circuit. We've got a lot of tiny little fine wires inside that circuit, and we don't want to melt them. So we mix in tin and lead and silver and all these different metals at the right mixture to have a really low melting point. So you can get some of these melting points under 200 degrees. And so it's really nice. So this is the if you go back to this phase diagram, following A all the way down is on this chart. So this is what the temperature would look like over time if you're cooling this. So it begins to precipitate some B, and then it pauses here, and that's called the eutectic pause. And then now you're cooling the solid. If you're at the eutectic, then you don't have any of this B precipitation region. You go along, you get a sharp freeze, and then you're cooling the solid. Now the reverse is the melting point. So at the eutectic, you're warming up the solid, then you have a sharp melting point, and now it's all liquid, and you're warming up the liquid. Whereas any composition towards that other isopleth, you've got this eutectic pause, and then you've got a really slow, long melting range, and then you're warming up the liquid. Sometimes you get down into the cold regions and you make compounds. So they call these reacting systems. This is A, B, and C, and essentially the compound AB is a compound with its own distinct melting point. So it has an actual, complex, like a molecular formula if it's atoms, but a lot of times these are just complexes. And so C is its own compound. AB is actually what we're calling C in this diagram. And it has a distinct melting point. So because it has a distinct melting point, you could have eutectics on either side. And so this is no different than the previous phase diagram, only they're two side by side. There's the compound AB, which I'll just relabel this AB. And so if we're following this isopleth and we're cooling down this solution that is about 60% B and 60% B, 40% A, what's going on right here? It goes to the nearest vertical line. And so this is what's precipitating. And so let me draw this one right here. I'm going to draw this over here. So if we had this in our little microscope, we would see little grains of AB, solid, forming. And then liquid, so A, liquid, and B, liquid. I should just do that. So we have A and B liquid mixed together and AB solid forming. Can you get that from the phase diagram? You come down here, you're hitting this melting, freezing line, and as you continue to cool, you're just making more AB solid. At this point then, you have the eutectic pause, and you start to form some pure B. And so eventually down here, you have this picture, let's draw it right here, of some AB solid grains and AB grains, and then B solid around it. And you would see that in a micrograph. If you took that solid then and you sliced it, polished it, looked at it under a microscope, used polarized light or whatever, however you could see the different grains, you would see chunks of AB that had precipitated out and then B that had frozen around it and held it together. And that might be the material that has the best properties that you want to be on that side of the AB composition line. Or maybe that's bad. Maybe B is weak and fractures, and so you want to be over on this side. If you're over here, then you have AB solid and A around it. If you're over here, you have A solid being formed and liquid A and liquid B. So when you hit that line, you just go left or right to the nearest vertical line. If I'm over here, cooling this one down, I hit that, then pure B forms, and then the liquid line follows this. If you catch that principle where wherever you hit, you go to the left or the right to the nearest vertical line, then you'll be fine. Don't skip that line and go on further. Don't hit this one and go all the way over to A. You're stopping at the next vertical line, and that's the AB line. Let's look at one that's experimental. This is sodium and potassium. So very similar metals. You've got potassium and sodium, alkali metals, and they will form a homogeneous liquid mixture here, at the top. And homogeneous solutions. So here's dirty sodium, and here's dirty potassium. Okay, let's follow this isopleth A1. So we go to the nearest line. Now, what is this line here? That line right there is actually a solid of dirty sodium. So in the experimental curve, there's these lines go diagonal. Anyway, let's follow this down a little bit further. We get down to here, and we've got, again, dirty sodium, and we've got this liquid over here. Eventually, when we cool below this line, we've got dirty sodium, and then we've got a compound. This compound Na2K. So that's actually a compound, a solid compound of Na2K. If you were to look at a micrograph of that, you would see crystalline domains of NAK. We call it NAK, NAK, but it's Na2K. And so then you have solid regions of Na2K and then solid regions of sodium, and those solid regions of what we'd say near pure sodium have some potassium contamination in them. Yeah. And as you go down, that you still have the Na2K and you have that potassium, dirty sodium. This Na2K though is present in the solid, but it doesn't have a defined melting point. And so that's what's going on in this slide. So you have the incongruent melting. You can't get a melting point for Na2K because it decomposes right here. So that's the decomposition temperature for Na2K, but it splits apart and then you just sort of change the nature of the solid line. And so it doesn't have a defined melting point. So that's called incongruent melting. Let's look at substances, reacting substances that do have defined melting points. And so here's calcium and silicon. So pure silicon melting point is here. Pure calcium's melting point is here, 842. Ca2Si has a melting point of 1314. CaSi at 1324. CaSi2 is incongruent melting. And so it comes up here and it decomposes. It has a decomposition temperature, but it's really not a well-defined melting temperature. Because if you were trying to get this melting point, you would not ever see a sharp melt. It would just be this smooth curve all the way up,
So which line does it decompose at? The top one or the one right below it?
It's this 1040. The 1030 is this eutectic temperature here.
Oh, okay.
And so this line right there shouldn't be there. That little bitty tiny line is so
okay.
hard to see. But yeah. And so this is pretty interesting. You've got silicon that melts at way up here. I don't even see the temperature listed. It's almost 1400. And here's calcium. You just put a little bit of silicon and calcium. Silicon has such a hugely high melting point, but you put some in calcium and it drops it down to 792. It drops at 50 degrees.
Drops it before it gets higher.
Yeah, it's so strange. So you just put a little bit of this high melting silicon into calcium and you actually drop why does it drop? Entropy. Again, a lot of this behavior is entropic. And so you make something impure, it gets a lower melting point, and it favors a homogeneous mixture. So, yeah. But this is probably the most interesting one that we have, because we have, if we call silicon A, then we have A2B, AB, and AB2. And so this is 33%, this is 50, and 67. So when you see lines on 67 and 50 and 33, you know it's an AB2 or an A2B or an AB. Wake up and catch that, because that's going to be one of those classic questions. When you see a chart like this and you see a vertical line at 67%, you know what the composition of that is. It's AB2 or A2B. And you just figure out what's being plotted on the x-axis and you can come up with that composition. Then we've only been dealing with two components. Here's three components: chromium, iron, and nickel. And these are different grades of stainless steel. And it just gets crazier and crazier. Okay, I won't test you on this one. But I just wanted you to see that after all of this, we've only done two components, binary mixtures. And it's just crazy, isn't it? The world is so interesting. All right, well, we'll see you next time. Didn't have time for the Kahoot.
We're